Alright, so the universe, it does not like me. I apologize. Apparently I ran out of space on my camera and it cut me off. So, this is a direct continuation off of our graphing video from last time. What I said that the camera lost. Velocity. Velocity is displacement over time, so we are looking at not only the magnitude, the speed, but also the direction. So if I were to draw a graph of that same car, the car is going in the forward direction, the positive direction, and he's going along at a constant speed, a constant velocity, because we're in the same direction. It is a straight line, just like the speed graph, and if he were to accelerate to get onto the on-ramp, we would show that again as an increase in magnitude in that positive direction. Technically, while speed, acceleration according to speed is only a change in the magnitude according to time, since velocity involves both a speed and a direction, acceleration from a velocity can be a change in either magnitude or direction. So if I were to left turn all of a sudden, going the same speed that I was before, that is still considered an acceleration because we have changed the direction. On graphs like this, most of the time we are looking at that magnitude, but not always. I can change my direction if all of a sudden I want to go a different way. So acceleration can be either one of those. So again, just looking at a couple of more examples of this speed versus velocity thing. So speed graphs, we're looking at how fast they're going. So if we started from 0, let's say you started from your house and you accelerated slowly down your street, you went a constant speed for a little ways down your street, and then you decided you needed to go back, so you turned around and you gunned it as fast as you could. The fact that you turned around on a speed graph is irrelevant because we are only looking at that magnitude. However, on a velocity graph, so once again, you come out of your driveway and you're accelerating slowly, you go down your street for a little ways, and then you turn around and gun it in the opposite direction. Because you have turned around, my velocity is now negative. I need a negative slope in order to demonstrate what my car was doing. So you need to make sure that that next piece is in fact a negative slope. That can be tricky because this bit here would show us slowing down, but instead we need an acceleration in the negative direction. Alright, real quick, let's talk about acceleration graphs themselves. So, the nice thing about acceleration graphs is the fact that there is no change, or a change in acceleration isn't another function. That's kind of all we got. So, back to the story we just told about the car that accelerated forwards, or you accelerated out of your driveway. Since you accelerated out of your driveway at a constant acceleration, that's whatever that value is. Since acceleration is not changing, it is in fact a flat line. When you go that constant speed or constant velocity down your street, there is no acceleration. So notice that we are creating a piecewise function here. The same can happen if you're looking at a velocity or a speed graph that does not include speeding up or slowing down. But since our directions, positive and negative, are indicative of direction, if I accelerate out of my driveway and then I drive down my street and then I turn around and haul butt the other way, if I'm hauling butt the other way, if I was at first going in a positive direction, if I turn around and go the other way, that is in fact a negative direction. However, here's where things get tricky. The word deceleration is tricky. Deceleration, in common vernacular, means to be slowing down. To be slowing down is truthfully to accelerate in the opposite direction. So if your car is going along and then he slows down, technically that means that there is a force acting in the opposite direction. So I am accelerating in the opposite direction, in this case, the negative direction. So to slow down is a negative acceleration. To speed up in the negative direction is also. So if we go faster in the negative direction, that is also negative acceleration. So when we're looking at these graphs, you actually need quite a bit of information. Oftentimes, the graph itself is not enough. It can give you an idea of what's going on, but it cannot tell you exactly without some extra words or some extra doings. Something I forgot to mention before. Back up here, where we had a change in displacement over a particular time interval, is our velocity. So this represents a constant increase. There's a constant slope here. That was represented by a constant line on my graph. What happens here, where I have an increasing velocity? So that means I'm covering more distance with each second. To look at the displacement versus time graph, whenever you have an acceleration, it will actually be a curve, an exponential function. That's something in my class we don't do a whole lot of calculating with, per se, but more in my course anyway. I want you to be able to recognize the fact that you're covering more distance with each passing second, so this is an acceleration, a going faster. In this case, in the positive direction. All right, so that is a quick introduction to the graphs, what they mean, what the directions go. In the next video, we are going to look at translating from one graph to another. So going from a displacement graph to a velocity graph, going from a velocity graph to an acceleration graph, and so on. So take care, happy graphing, and see you next time.